Hello and welcome back. Today we're going to be continuing on in the same vein as where we left off with our segmentation and memory virtualization. And that continuation today is going to be in the form of paging. Now you'll see that paging, when we get into it, shares many similarities with segmentation, as well as the base and bounds approach for memory virtualization. But it also looks to solve some of the problems we identified with respect to segmentation through its approach of address translation. So just a quick recap from last week. We looked at a couple different concepts before. Firstly was like how does the CPU virtualize its memory? And that was the concept of the address space. Secondly, it was how to translate between virtual addresses, which were the addresses in the address space, and physical ones, which were the addresses in actual physical memory. And thirdly, we also looked at segmentation, which was a slightly different approach to the base and bounds approach. And that approach also had a slightly different take on how we do address translation. And lastly, we looked at how do we allocate memory regions, like allocated memory and free memory, as well as how do we keep track of our free memory, and that was through the use of that free list. So moving on to today's concept, which is paging. And paging will take up the whole of today's lecture. Both parts 1 and 2 will be revolving around paging. So what is paging? Well, in operating systems, paging is a storage mechanism, so similar to segmentation, used to retrieve processes from secondary storage into main memory in the form of pages. And the main idea here is that paging is a process where we divide each process, so each process in memory, specifically referring to the address space here, into a fixed sized unit called a page. And the difference here between segmentation and paging was that in segmentation we had those variable sizes for logical segments, right? The code could be the code segment in one process could be a different size to the code segment in another process. The same for the stack heap, etc. Whereas paging specifically a fixed sized unit. And with paging, physical memory is also split up into a number of pages, and these are called page frames. So the address space is split up into pages, and the physical memory space is split up into page frames. Okay, so immediately your question is, okay, well, how does this affect our translation? How can we go from virtual to physical utilizing this paging approach? Well, there is a data structure called a page table that is needed per process to translate from our virtual to physical addresses. Now, this page table works similar to the segment register. And if you remember, the segment register was basically a way of it was utilized to translate from virtual to physical, where you would use the base and its size, or basically a base and bounds register value per segment. Now, the page table is slightly different. So our page table is simply like a lookup table, which tells you, given the pages, which page frame are they associated or mapped to. And because there is a page table per process, all of the pages on the left-hand side here, you'll never have duplicate values, right? Because we're only looking at per process. And they're only mapped to a specific page frame. So here page 0 is mapped to page frame 3. So page 0 for this specific process in the address space of that specific process is mapped to a physical address page frame 3. And we're going to be looking at a little bit later an example of how we actually utilize this. So just before we get to that example, I just want to explain some of the advantages of paging. Okay, so the first example is flexibility, in the sense of supporting the abstraction of the address space effectively. So with regards to paging, we don't need to know how the heap and the stack grow. If you remember to segmentation, when we elaborated a bit on it, we discovered that we needed to have a bit register or a register that kept track or indicated how the heap and the stack grow. In paging, we don't need to worry about that. The second advantage is simplicity, and this is simplicity in terms of its free space management. And this is a result of the one benefit in terms of the page and the page frame that it's mapped to are exactly the same size. So if a page in the address space, or if all the pages in the address space are like 25 kilobytes, well then all the page frames in the physical memory space will also be 25 kilobytes. And we'll see later how this actually benefits when it comes to address translation. The second sub-benefit here is that it's easy to allocate and keep track of a free list. And again, we'll look into that a little bit later. Cool. So an actual paging example. So here I've laid out our physical address, or our physical memory, as well as our address space of a particular process. And you can see on the right hand side here, our page frames are all being labeled, and all of the different blocks here are our different pages. So what does this example tell us firstly? Well, it says that we have 128 byte physical memory with 16 bytes page frames. So this 128 byte physical memory is divided into chunks of 16. So if you do the math, like 128 divided by 16, that will give you 8. And you can see here we have 8 page frames. And then we also see that our address space is of size 64 bytes, and it is also divided up into 16 byte pages. So each of these pages here is its own 16 bytes. And these pages will be stored in physical memory, of course. And you can see that page 0 here, which is from 0 to 16, or 0 to 15, is stored in page frame 3. Page 1 is stored in page frame 7, page 2, page frame 5, and page 3 in page frame 2. Now usually the operating system will take up the initial page frame, and it might take up multiple, but in this case it's just the first one. But this is exactly how the mapping would be. So if you wanted to translate like page frame 0, it will obviously be mapped to page frame 3. Sorry, if you wanted to map page 0, it will be mapped to page 3. And this is the stuff that is indicated in our page frame table, or our paging table. So let's go into this example a little bit more and handle an actual address translation. So now our virtual address will have two components. The first being a VPN, or virtual page number, and this indicates basically which page it is inside the address space, as well as an offset. So within this specific page, where is this specific address? So if I just go back quick, so say it was page 0, so my VPN would be, say, 0. Then the offset is within this page here, which actual address. So we'll add a value to our page number or our VPN and get that offset. Cool. So that's what VPN and offset is. Similar to how segmentation worked, with the base plus the offset. Okay, so here we have an example of a virtual address, specifically virtual address 21 in our 64 byte address space. And the virtual address is then translated or transformed into binary, and you get 010101. Now, questions you might be asking is, well, how did I get that? How did I get 010101? And how did I know that my address here is 6 bits long? So you can see I have 1 bit, 2 bits, 3 bits, 4 bits, 5 bits, 6 bits. How did I know that? How did I know that there was a 0 at the front here? These are all questions I will answer now. Okay, so on to that first question. That being, how do I know the virtual address is X bits long? Well, here we basically have to think about it a little bit. So I have a 64-byte address space. So I basically have 64 addresses or values that I need to store in a binary string. And the question is like, how long is that string? Okay, well, if I have 64 different values, what is the smallest binary string that could represent that? And our binary values can have only, right, it's binary, so it's either 0 or 1. So each of those bits only stores one of two values, either the 0 or 1. So all we do is we take our address space size, so here it's 64 bytes, and we take log base 2 of 64, and that gives us 6. And if you want to see why this works, if you take 2 to the power of 6, you'll get 64. Okay? And that makes sense, right? Because we want to store 64 different values in the lowest amount of bit space, or the smallest bit string possible. So if you take the value 63, so this is we counting from 0 to 63, which gives us 64 different addresses, and we convert that to binary, you'll get 111111, our like maximum address with 6 bits. Okay, so that's how I know that this was 6 bits. This is how I know that the 21 needs to be converted to an address of length 6 bits. Okay, so now that I know that the whole address needs to be 6 bits, how do I know that it's 2 for the VPN and then 4 for the offset? Well, this is when our page size comes into play, and we basically apply the same approach. We know our page size is 16 bytes, so all we do is we do the same thing. We take log base 2 of 16, and that will give us 4, and that is our offset. Okay, because we have 16 addresses within a page that we need to store information for. And once again, if you convert 15, the value 15 into binary, you'll get 1111. So we have 0 to 15, and that can be stored in 4 bits. Okay, so if the offset is 4 and the total length is 6, obviously the VPN needs to be 2. Okay, cool. So what we can do then is, well, now I take my 21 and I convert it to binary. So 21 in base 10 is 10101 in base 2. It's only 5 bits, but I'm storing it in a 6-bit value or 6-bit register in our virtual address. So I just put a 0 in the front. So now the 01 becomes our VPN, and the 0101 is our offset, as you can see here. So that's how I got the virtual address in its proper form. Okay, but that's only half of a translation, right? We need to go from the virtual address all the way to the physical address. And that's what we're going to do. So, some things to note when we're doing the translation. We must remember that our page frame and our pages are the same size, but the size of our physical address space and the size of our the size of physical memory and the size of the address space is not the same. So that's where the translation occurs. Now when we're doing the translation in paging, our offsets, once again, because the page size and the page frame size is the same size, the offset remains the same. So we could just carry that down. Okay, so when we had 0101 offset in our virtual address, the sizes are exactly the same, so the 0101 becomes our offset in the physical address. Okay, but how do we know that our PFN now, or physical, or page frame number, sorry, is 111? And also, how do I know that it's 3 bits? And how do I know that the whole address here is 7 bits? Well, as you can see in that little calculation, we know that the physical address space is 128 bytes, So we just apply the same approach. Okay. We need to store 128 different address values. So what is the lowest or smallest bit string that can store that? Well, it's 7 bits. Once again, we just take log base 2 of 128, and that gives us 7 bits. Okay. So, well, that means that our offset we know is 4 because it's just carried down. Our total length is 7. So 7 minus 4, we know that our page frame number must be 3. Okay. And here I just simply said that there's this address translation step that happens that gets the 01 to the 11. Okay, but let me elaborate a little bit on how that actually works. Cool. So if you remember back to a previous slide here, we had our physical memory and our address space represented. So let's take, for example, that in the example that we've been working with, that this is how the memory is laid out. Okay, we know our VPN is 01 because that's what we calculated. And we know that our page frame number is of size 3 bits. Okay. So where is our VPN? It's telling us that it's 01. Okay, so that means that it's this page here, because if this is 00, the next one's 01, the next one's 10, and the last one's 11. Okay, which makes sense because our VPN's only 2 bits, so we couldn't ever have any more pages than this because you wouldn't be able to identify them. So we know that we're working with this page 1 over here. Okay, and here we can just visualize, right, which page frame it's related to. We know it's this page frame 7. Okay, well that makes sense because we can actually see this translation. So visually we can see that it corresponds to the last page frame 7, and that is in essence the 8th page frame, right, because we start at 0. So it's 0, well it's 1, 2, 3, 4, 5, 6, 7, 8. So this would be the 8th page frame. Okay, and what we can do is we can convert the value 7 into binary and you get 111. Okay, so we know that page frame 1 is mapped to, we know that page 1 in the address space is mapped to page frame 111. So that's exactly the translation that you need to perform. So here we see that our virtual address of 01, the VPN, the virtual page number, which is 01 for our virtual address, through our, in this case we use like a visualization approach, we got that the page frame number was 111. So that's pretty easy when you can see the actual mapping, right? But how does the operating system see that mapping, and how does it set it up to be used in translation? Well, if you remember back to those definitions that we used, we learned a little bit about what is called the page table. And we learned that there was a page table per process. And that is what is used to perform this translation step. The translation step between the VPN and the PFN. So if you remember here, page translation, we got this page table, right? Where we knew that 0 was mapped to page frame 3, page 1 was mapped to page frame 7, and that's what we looked at, right? That's what we saw in the example now. So the operating system uses this table, which is stored as well, and it's stored within the OS, the kernel itself, to perform that final step of translating the virtual page number to the page frame number. And that's how you do the address translation. So that's how you go from our virtual address in address space to our physical address in obviously the physical memory. I hope that makes sense. Okay, well, I alluded to this a little bit, but where are these tables stored? And this brings up a little bit of the problem when it comes to paging. And the reason for this is that page tables can get large quite quickly, right? When you have many more pages, shall we say. So if you have like a 32-bit address space with 4 kilobyte pages, so not very big pages in today's age, there is 20 bits for the VPN now. So we were only working with like 2 bits for the VPN, but in this case now there's 20 bits for the VPN. So if you do like a quick calculation here, that each page basically is 4 megabytes. Sorry, each page table becomes 4 megabytes. And that's 2 to the power 20 entries times each page, okay? Or the size of each page. So this is how many pages there are times the size per page table entry. Sorry, not per page table entry. And this is just far too large to store entries in a dedicated like CPU register. And that's why we store it in the operating system kernel, in memory itself. Because if you think back, our base and bounds register, those were just 2 values that you needed to store, right? So you could have a register to store those, but we can't have a register that stores this much data in the CPU anyway. But it can be stored in memory. So now if, say we have 4 processors all in memory, there will be 4 page tables all stored in the operating system kernel. So in page frame 0 hypothetically. So yeah, when a process is loaded into memory, its page table is generated and created and then stored in the kernel. And that makes sense because the kernel is doing the translation because it is a privileged action. So it's handy to have that within kernel memory anyway. Because if you had it in, say, process space or the user space, processes themselves could manipulate the page table to point to other pages in order to, get use of memory that isn't allowed to them. So page tables are stored in the kernel. And just to elaborate on what is a page table, it's just a simple data structure, kind of like an array, that is used to map a virtual address to a physical address. And it specifically stores the page numbers and the page frame numbers that it's associated with. And like I said, in its simplest form, it's just an array, right? The indexes will be the page numbers, and the value that you get out will be the page frame numbers. Yeah, and that's exactly what I said. So in the case that I've described here, a page table entry, it will just be the page frame number. However, in practice, this is not necessarily the case. There's a lot more information that goes into a page frame entry. So when I say page frame here, it should actually be page table entry. And on the next slide, I'll show you everything that can go into this page table entry. So here we have an example of a x86 architecture example for a page table entry. And obviously there's a page frame number, just like we demonstrated here. We need that page frame number to do the translation. But it also has all this additional stuff. It has a present bit, a read-write bit, a supervisor bit, an access bit, a dirty bit, and the page frame number. And this is just to name a few. And these aren't super important to know, but the next slide explains a couple of them. So P, so it's this one on the far right here, is what they call the valid bit. And it indicates whether the particular translation is valid. We have the protection bit, which indicates whether the page could read from, written to, or executed from. So this is like a privileges bit, read-write bit. We also have a present bit, indicating whether this page is in physical memory or if it's actually in physical storage, so like on disk, if it's been swapped out. We have a dirty bit, indicating whether the page has been modified since it was brought into memory. And a reference bit indicating that a page has been accessed. So the valid bit and the present bits are basically one and the same. And different books will use both terms. One indicates if it's in physical memory or not, and the other one indicates if the translation is valid. The only time a translation would be invalid is if the page was not in physical memory. So you can see how they're kind of performing the same task. But yeah, so valid bit and present bit basically represent the same thing. Cool. So this is what an actual page table entry looks like, but we'll be mainly focusing on just utilizing the page frame number. Okay, so this sounds all very good. Translation's pretty easy. We can store a lot more information in smaller chunks of data. So what are some of the issues with paging? And that's what we're going to be looking at in the next couple of slides. Because it seems like it's a really good solution that takes advantage of segmentation and basically, or takes advantage of the idea of segmentation and runs with it a bit. And we've already said one of the issues, and that is size. Page tables and entries take up a lot of space in memory, because the more pages you have, the more page table entries there'll be, etc. The second one is it's slow. So there's where before we only had to access memory using one reference, there are now two references per memory reference, right? You have to reference the page table, and then from the page table you can reference the actual memory address. So that makes it quite slow doing these two references every single time. So let me just elaborate a little bit or explain better what I mean by this. You require two references per memory reference. So firstly, we need to reference the correct page table. So what is the correct page table in our kernel that corresponds to this particular process? So that would be the first reference, right? And what I'm saying here is to find the location of the desired page table entry, we need the starting location of the page table for that process. Okay, so we find the page table, all right? Then once we found the page table, we can reference the correct page table entry. So firstly, we look for the table itself, and then we look for the entry in the table. So that is two references. This means that for every memory reference, paging requires the operating system to perform one extra memory reference every single time. And this isn't very efficient. So how does accessing memory with paging actually look like in code? So I did this example for segmentation. So I'm going to do a similar type of approach for paging. So the process starts with, well, we need to get the VPN from the virtual address, and you extract it through this AND, or you take your virtual address and you AND it with the VPN mask, similar to like I've done before, and then use bit shifting to shift it so that you only have those the VPN bits. And then you can form the address of the page table entry, so our PTE, by taking the size of that VPN and adding it to the page table base register. So this points to like the beginning of the page table, and then this VPN times the size of the PTE is basically that offset, and then you can get the address of the page table entry that you're looking for. And you remember our page table entry had those additional things like a valid bit. So we want to check if we can access the page, and we utilize that valid bit. If the valid bit indicates that, if the valid bit is false, so we need to raise a segmentation fault. As well as we need to check if we can access the information. So we have the protection bit that lets us indicate if it's read-write accessible. And if it's not, then we once again raise an exception. And if we get past both of these checks, then we can actually access that physical address. And then you go through that process that I've outlined, where you get the offset, you then get the physical address, and with the physical address you can actually store the information at that memory location in some register. So that's how it would look in like a code sense. Let's go through another example of accessing memory with paging. So here we have a simple memory access example in terms of an array that we want to access each element of. So we define an array of size 1000 and we loop through it, setting each value to equal 0. Okay, you can make this code yourself and you can execute it. And if you're interested, the assembly code would look something like this. Now, it's obviously this assembly code that gets loaded into memory. I'm going to run through what this assembly code actually does and what it means, but it's not super necessary. This is just a bit of information if you're curious. So what ends up happening on the first instruction? Right, so it's kind of easy to understand, but a little bit complicated if you're not very familiar with x86 architecture, which I doubt you would be. I'm not very familiar with it. Now, the first instruction, this one here, moves the value 0 shown here of 0x0 into the virtual memory address of the location of the array. And this address is computed over here by taking the contents of this register and adding this register's value multiplied by 4. And the result of that means that the EDI register holds the base address of the array, whereas the EAX register holds the array index I. Okay? We multiply by 4 because the array is an array of integers, and each integer is a size of 4 bytes. Okay, that's how much space is required to store a single integer. So this step is basically like the initialization of our array and our index. Then the second instruction increments the array index held at EAX. Remember, we stored it there. And it increments it by 1. And then the third instruction compares the contents of that register to a hex value of 0x03E8, which is basically a value of 1000 in decimal. So here we're doing the check to see if our index is less than 1000 or not. Okay, so this is the compare instruction. And what we want to do, if the comparison shows that the two values are not yet equal, so that our I is not equal to 1000, so in the fourth instruction, so if the comparison between the two values are not yet equal, the fourth instruction will jump back to the top here, to this address basically, and the process will continue again until a time where these values are equal, so I is equal to 1000, and then it will stop. Because this is saying jump not equal. Okay, so that's basically what the assembly is doing, the assembly code. This is setting the value equal to 0. This is incrementing our I value. This is doing a comparison. And this is jumping whether or not that comparison was true or false. So to better understand which memory accesses this instruction sequence makes, so the sequence of assembly code instructions that we described in the last slide, we will have to assume something about where in virtual memory the code snippet and the array are found, as well as the contents and location of the page table. So what I'm going to be walking through here is a memory trace in both the physical and virtual space. So for this example, we'll assume that the virtual address space is 64 kilobytes, which is quite small in normal. We'll also assume that the page size of 1 kilobyte for each page in the address space. And all we need to know now are the contents of the page table and its location in physical memory. So let us just assume that it's an array-based page table. So like I've been describing before, where you use the page number as the index value, and then the page frame number is, or the page table entry is the output value. So we're just going to assume it's array based, and we're going to assume that it's located at the physical address 1 KB. So you can see here the physical address 1 KB, which is 1024 in bytes. Okay, and that's going to be the beginning of our page table. So page table entry 1 will be at that address. So you can see here I've circled it. Okay. As for the contents, of that page table, there are just a few virtual pages we need to worry about. That we need to worry about having mapped for this example. First, there is the virtual page that the code lives on. Now, because the page size is 1 kilobyte, the virtual address 1024 resides on the second page of the virtual address space, so VPN 1, as VPN 0 is the first page. So here we can see it's just above 1024. Now it's kind of hard with the squares, I get it, but it's just above 1024. And let us just assume that the virtual page maps to the physical frame 4. So VPN 1 is mapped to page frame number 4. So a lot of these setups isn't very important, but the end conclusion that I'm going to make is just what you guys really need to understand. Okay, then the last thing we need to know is information about the array itself. So it is of size 4,000 bytes because it's 1,000 integers. Each integer takes up 4 bytes. And we assume that it resides at the virtual address 40,000 all the way to, well, 44,000 excluding the last byte. So that's what you can see here. So our array starts at 40,000 and it will go all the way to 44,000. Now the last thing we just need to talk about a little bit is the virtual pages that represent where that array are stored. So for this example, the virtual pages for this array range are VPN 39 to 42. Thus we need mappings for these pages. And let's assume that these virtual to physical mappings for the example are VPN 39 to page frame number 7, 40 to page frame 8, 41 to 9, 42 to 10. Okay. Again, these numbers not super important, but if you want to go deep into this example, then you can look at that. Okay, so we are now ready to trace the memory references of the program. So you can see, obviously in the code segment, we can see those code instructions that are there. And this one here, this MOV instruction, is obviously the one that relates to accessing the array. So that's why you can also see it here in this array component. Now, when it runs, each instruction fetch will generate 2 memory references like I've been talking about before. One to the page table. So in, for example, this first instruction here will generate 1 reference to the page table. In this case, it's page table 1. And this is the page. This is to get the page frame that the instruction resides within. And 1 to the instruction itself. So it will be 1 reference here as well as 1 reference to the instruction itself. Okay. In addition, there is 1 explicit memory reference in the form of the MOV instruction. So this MOV instruction explicitly references a specific address in memory, and that's like the address of the array at that particular index. So there's another instruction reference here, or sorry, memory reference here in this case for this MOV instruction. So this adds another page table access first. So to get to this location, you would first go through page table 39 as set up in an example there when I was talking about it. So there's basically, for this first instruction, we'll have 1 access to this page table, 1 access to the actual instruction, 1 access to this page table, which will allow us to access this location in memory. So for this first instruction, there's actually 4 references happening. Okay, and then each and every instruction will then be processed. So what are these graphs actually representing? Well, the bottommost graph shows the instruction memory references, and on the y-axis, the virtual address on the left, and on the right hand side the actual physical address. So here the virtual address is on the left and the physical address is on the right. And if you're paying attention to that setup that I was doing beforehand, that's why these values are as they are. But again, it's more important that you get the understanding of how many different memory accesses are occurring. Now the middle graph shows the array accesses, again with the virtual on the left and the physical on the right. So we have virtual and physical. And the topmost graph shows the pages, or the page table memory accesses with just the physical on the right hand side. Because in this example, the page table resides in the physical memory in that kernel space. Now, what does the x-axis represent? Well, the x-axis for the entire trace shows the memory accesses across the first 5 iterations of the loop. So you can see here's the first iteration of the loop in terms of instruction accesses. Here's the first iteration up until this point of the loop in terms of array accesses. And here is the first iteration of the loop in terms of page table accesses. So here you can see that for one iteration of the loop, there are 10 memory accesses per loop. And that includes, we have here 4 instruction references, okay, or 4 instruction fetches, 1 explicit memory update, which we can see here, and 5 page table accesses which were required in order to translate these addresses from virtual to like the physical. So hopefully this gives you a better understanding of how many actual memory accesses are required to perform that that simple function of looping through an entire array, right? Again, the general, like these last couple slides probably seem a little complicated, but the idea here is that I just want you to understand the different accesses of memory that are occurring. And you can see here, in order to just perform one loop here, we are doing 10 memory accesses for roughly 4 instructions. So that is obviously quite inefficient. So now as you have like a better understanding how memory is addressed through paging, you can get a sense of why we say that paging is slow. Now, what are some of the techniques that we can apply to increase the efficiency of accessing memory? Well, what if I told you you already knew some of these techniques? And if you think back to first year, that you actually described these techniques already. So when asked about, for example, what are the advantages of arrays? And your answers would be, well, spatial locality or temporal locality. And that's exactly it. Those are the benefits that we can apply, or those are the techniques rather that we can apply to make paging a lot more efficient. And that's what we're going to be looking at in the second part of this paging lecture. And in that lecture, we'll be looking at what is called the translation look-aside buffer. Otherwise, thank you for listening. I know we ended on a fairly complex or difficult to follow example, but it's merely to demonstrate how many actual memory accesses are required to perform relatively simple tasks.